All right, on this lovely day, we're going to be working through work and mixture problems. So we're going to create and solve linear equations using one variable. Before we do that, one skill we need is to be able to convert decimal time, like 2.4 hours, to practical time, 2 hours and 12 minutes or 13 minutes or something like that. So that's what we're going to spend a moment here doing. The first thing we're going to do is you take the hours, the 2 part, because that's already an hour. So I can actually bring that down. The 2 part is 2 hours. So I need to consider now how many minutes is the 0.4 of an hour. So mentally, what we need to consider is that this is 4.4 hours. And what we have to do is we need to multiply that by 60 minutes per hour. I'm going to write the units here just so that you can clearly see. If I have 0.4 hours and I have 60 minutes in an hour, that's my conversion, my exchange rate, so to speak. Notice what happens here. Because the hours, one is in the numerator and one is in the denominator, the hours reduce. They cancel out. So now what we're left is minutes. So when I do the product here, 0.4 times 6d, we're going to end up with the minutes. When you do calculate this, I get 24. It's a whole number. There's no decimals, so I don't have to do anything further. So that means 2 hours and 24 minutes. And if you're writing it with h's, then you can also just write it with an m, like this. 2 hours, 2h, 24m. Or you could write it all out if that cranks your tractor. So that first problem was very straightforward. 3.8 weeks, we're going to do that algorithm over and over and over and over again until we get down to, we might even get down to seconds. So 3.8 weeks, what is that practically? So first thing we note is we have 3 weeks. So I can write that down, 3w. I need to take the remainder, the 0.8 weeks, so I'll use w there. So w is not a variable here. W is my unit. And we need to ask ourselves, when we convert it, what's the next unit that goes underneath weeks? Weeks. Now we need to convert from weeks to days. So I'll put 1 week down on the bottom and 7 days on the top. In other words, 7 days a week, unless you are the Beatles. 8 days a week? Did they have a song about? Anyways, Hard Day's Night, the Beatles are all messed up. In fact, their name's even spelled wrong. All right, now the W's cancel out, ka-chow here, and all we have to do is with our calculators multiply these two here. So this here gives me 5.6 days. So our algorithm has to repeat. I'm going to take this 5 right here and say 5 days, and the 0.6 has to be converted. So now we do it again, but with a different conversion. 0.6 days, and now what's the next unit that we are dealing with? What is underneath it? Hours. 24 hours in 1 day. Now, I'm writing all this out so you can see it, but when you do the algorithm with your calculator, you actually don't need to do all this crazy work. Again, we're writing it out so that next time you check your notes, you can see where it comes from. So, again, the days will reduce here, and 0.6 times 24 will give me hours. 14.4 hours. So I write the 14 down with the hours. Now I have to take the 0.4, 0.4 hours, and convert that. 60 minutes per 1 hour. And when I do multiply this out once again, my hours drop out. I'm left with minutes, and the calculation is 24 minutes. So, to read the final answer is this. 3.8 weeks is equivalent. It's the same as 3 weeks, 5 days, 14 hours, and 24 minutes. Now that we have that in our toolbox, let's look at a scenario about what work problems, and this same thing here has to do with mixture problems too. But work problems are where you're working together. So let me just read example C just so that we can see some context, okay? You and your sister must rake leaves in the backyard. Since you've done this so much, you have a good idea that you can do this in 2 hours. Your sister, being younger than you, will probably take 3 hours. So had she done it by herself, it would take her 3 hours. So the question is, what if you rake together and you're not distracting each other and you're not playing, monsters or whatever with the leaves and you're not jumping in the leaves? So assuming you're still working well together, without all those social crazy things, how much time do we expect it to be? So our estimate of this would not be the average of those two, but actually be clearly lower than that because this can be done at faster. So here's pretty much a work problems equation, all right? So this right here is we're going to talk about getting our job completed. So in the end, together, we do one job. One job, whatever task it is, one task, one job. That job could have different things: raking leaves at a yard, cleaning up crime in all of Gotham City, painting a house. Whatever that one job is, it's one job. So we're going to call it one. Now, in this case, I have 2 people. There are 2 people in my scenario. So when I consider how much work or how much of the job, this is the piece of job for worker 1, in this case, you. And then over here is my sister, or your sister, is going to do a piece of the job, a part of the work from worker 2. So when we look at this part of the job and this part of the job, together it's one job entirely. So let's consider this one once again. You and your sister must rake leaves in the backyard. You can do the job by yourself in 2 hours, which means in 1 hour, I can do a piece of the job. In 1 hour, I can do half the job. In 1 hour, I could do half the job. In 1 hour, she can do 1/3 of the job. So, since we're both going to work the same amount of time, because that's the question, how long? So the time here, time working. If I can do half the job in 1 hour, then I'm going to say 1/2 t, or t over 2. We can say it that way as well. And over here, she's going to work the same amount of time, but she's going to be working at a rate of 1/3 of the job per hour. So essentially what we've just done here is this is the rate per hour, not how much money you're making, but how much of the job. In 1 hour, I can do half the job. In 1 hour, she can do 1/3 of the job. And together, we do one job. Now, the skill, of course, that we've looked at before is how do we get rid of all the fractions here? Well, if I look at the left side here, the left fraction, to get rid of this fraction, I have to multiply by 2. But to get rid of this fraction, I have to multiply by 3. So what super secret number can I multiply? One number that gets rid of both the 2 and the 3. So if I multiply everything by 6, which is a common multiple of those two, just multiply this by 6, this by 6, and this by 6. So each element is being multiplied by 6. As we do that, let's see how things reduce. 6 divides by 2 to give me a 3. So I bring down the 3t. Bring down the plus. 6 divided by 3 gives me a 2. So I bring down a 2t. And 1 times 6 is 6. When we combine like terms, we get 5t, and I'm running out of space here. To get 5t equals 6. And now we divide by 5 on both sides. I'm just going to do that over here. Do I just say 6/5 and I'm done? No, not really. because 6/5 doesn't actually make sense. So you're asked, so how long is this job going to take? Oh, 6/5 of an hour. Huh? No one talks like that. So let's bring that back into the real world. So as I work on a conversion over here, 6/5, remember what 6/5 is. 6 over 5 is equal to 1.2 hours. So now, like we said before, I take the 1, write it down, and then I take the 0.2 and multiply that using my calculator. So when I multiply the 0.2 by 6D, then I get 12 minutes. So the answer right here is how long will it take? 1 hour and 12 minutes. Some of us estimated hour and a half, something like that. Good. At least we were on the right track. If you had estimated 2 or 3 hours, or you said, oh, well, together, 2 plus 3 is 5, that would logically not work. So the process I did here was to say, in 1 hour, how much work can each person do? Half of the job, a third of the job. We combined their efforts together to make one complete job. So that's our nice setup. Kill the fraction immediately. And then from there is a very straightforward scenario. So walking through this, number 1, how many liters of a 14% alcohol solution must be mixed with 20 liters of a 50% alcohol solution to get a 20% alcohol solution? So conceptually, here's what's happening. We have 20 liters of the product, which is a 50% half alcohol. We're going to add a much more diluted, a 14%, so it's closer to water, and we don't know how much or how many liters we're going to add. But in the end, we're going to get a 20% solution. But notice that if I did add this much water, or solution, plus this solution, I'm going to get a larger amount of solution there. So 20 plus the X is how much end result solution we have. And it's a 20%. What's nice is that once you have it set up conceptually like this, the product of these two right here tells you how much actual alcohol you have. So 20 liters times 50% gives you how many liters of alcohol available. Same thing here. And then lastly, 20 times this 20 plus X. Now you can keep it, you can do it in terms of converting the decimals, the percents to decimals, or you can just ignore that entirely and just start right here like we did. 50 times 20 plus 14 times X equals 20 times 20 plus X. When we keep working through that and we do our distributive property, we get 1,000 plus 14x equals 400 plus 20x. Now I'm going to collect my variables by subtracting 14x from both sides and 400 from both sides to get 600 equals 6x. So x is 100. So practically speaking, I need to pour 100 liters of the 14% solution in. As we read this one, let's pay attention to 2 or 3 key differences besides the products themselves, just the concepts behind it. So chocolate coffee beans sell for $7 a pound, and a hazelnut coffee bean sell for $6.10 per pound. A customer wants 6 pounds mixture of both types of coffee. How many pounds of each should be used if the mixture is to cost $6.40 per pound? All right, so if we still think about this in containers, we can. So I'm going to put these in containers again just to show you here. We don't know how much coffee is in each container, but we do know in the end that we want 6 pounds. So right here, that's 6 pounds. It's going to be 6 pounds, which means if this one is called my unknown, then this has to be 6 minus the unknown, right? It's the remainder. So instead of adding these two together to get a sum over here, or an expression that looks like a sum, I'm using these two to write this one as a difference. But everything else is the same. Instead of percentages, we're using dollars. So this one, for example, is going to cost $7 per pound. This one is $6.10 per pound. And over here, this one is going to be $6.40 per pound. So all we have to do is set up it in this same way. When we multiply these together, add them to these together, then that's going to give me the total value here. So we just need to know essentially how much of each of these do I need to get a 640 mix. It's a $6.40 mixed. All right, so bringing this down, we get 7 times 6 minus x plus 6.1 times x equals 6.4 times 6. All right, so now we keep walking through this, and I'm going to distribute out. So continue the work over here to get 42 minus 7x plus 6.1x equals. So after we distribute and multiply out, this is what we get. I can combine like terms here. So 42 minus 0.9x gives me 38.4. Negative 0.9x gives me 3.6. And that's a negative also. And when I divide here, I get 4 pounds. So let's just clarify which we're dealing with which. So the $6.10 per pound is the hazelnut. So I need 4 pounds of the hazelnut. So 4 pounds of the hazelnut, which means I need 2 pounds of the chocolate.